Hi, I'm Camryn,
And I'm Ryan.
and this is our final project for ECE 3710, in which we make an LED snake game.
This is the proposed block diagram for our initial design. As you can see, we have a microcontroller that's interfaced with an LED grid using I squared C, as well as interfaced with Joy-Con using I squared C. We decided to go with different designs due to constraints from our LED, so instead we decided to use SPI. Additionally, we decided that the design of using a Joy-Con for this game would be better if we used buttons instead.
So this is our actual block diagram for our design. On one side, you will see that we have 6 buttons. These control the inputs from the user for the game. These buttons are active low. They are configured with internal pull-up resistors in the microcontroller as inputs. And then on the other side, we have our 8x8 LED matrix. This connects with the microcontroller using SPI. So a little bit looking into SPI, or serial peripheral interface. This basically works by once the chip select line is brought low, the clock begins. And whenever the clock is brought up high, the device will latch in the data. And the way that the MAX 7219, the chip we're using for our LEDs, works is that it has 16 bits of data it reads. The first 4 bits don't do anything. The second 4 are the address or the column which we're writing to, and the last 8 is the data we're sending over. So this is a little look at what our SPI write function looks like. We had difficulty using the built-in SPI modules, so instead we just wrote our own function. And basically what it does is it loads in the data, turns the clock off and then back on, and then at the very end, after it's done our 16 bits of data, it turns chip select on and off.
This is a physical graphical representation of how our snake program works. As you can see, there is a snake body marked by integers as well as a yellow spot pixel with a 100 that represents fruit. There are 4 main functions that drive the snake game, and we are going to go into those now. The first one is the snake initialize function. This essentially creates an 8x8 array in which we can mark different integers to represent what's happening in the game. The next function is the move function. This will take in an input from the user and decide what the next location the snake is going to be moving into. It also checks for the bounds of the grid.
Now this brings us to our update snake function. This is basically what keeps the game going. And in the update snake function, basically we look to see if the snake, we first increment everything on the grid except for the spaces and the fruit, and then we look to see where the snake is moving. If it's moving to a spot with no fruit, if it's going to hit a fruit, or if it's going to hit something else like itself. And then at the very end of this function, we remove the last piece of the snake. Now this is our write snake to screen function, and this is how we actually print the snake to the LED grid. We start by having an 8x16 array, and this already has the addresses built in for us to use. Then we basically use a for loop to convert the last 8 spots of each array to be the actual data we want to write, and then we use the SPI write function to print each of the 8 elements of the array.
This is our main function. As you can see, the majority of it is just initializing our different setups, including the systic and the hardware interrupts. Then it sits in a while loop forever and waits for hardware interrupts from the user to trigger different states of the game.
Now this brings us to our systic interrupt. The systic interrupt has 2 states. First, it has if the game is not beginning yet, and in this point it shows the loading screen, and this works by updating the loading screen and then resetting it once our count is equal to 64. The other part is the actual running of the game, and this basically works by checking the buttons to see if the user has put in a direction, updating the snake, and then writing that updated snake value to the screen.
Here we have the two hardware interrupts for the speed button as well as the start button. The start button works by changing state if it is triggered, and if the game is over and the snake is dead, triggering this button will change the state back into the loading screen. The other interrupt works by putting a updated value into the systig load register in order to change the speed of the game. Lastly, these are the directional buttons. Here we have different cases that can happen. When you press a button, it'll sense into the input data register and change the direction that the snake is traveling.
All right, with that, we'll go ahead and get into a demonstration. This is the setup of our project. If you look below, the first thing you will see are the 6 buttons used to control the game. The 4 buttons at the bottom are our directional buttons, that being up, down, left, and right. Up at the top, we have our 2 control buttons, which are connected to the microcontroller as external interrupts. The blue button begins the game, and the yellow button selects the difficulty. The buttons are connected to the microcontroller as inputs, and they are internally pulled up. This means that the buttons are active low. One pin of the button is connected to ground, and the other pin is connected to the microcontroller. The next part of our project, we have our 8x8 LED grid. The LED grid connects to the microcontroller with just 5 pins. The first 2 pins are voltage and ground. The last 3 pins are the SPI pins, that being clock, chip select, and data in. Through this, the microcontroller is able to control a large amount of LEDs, that being 64 in this instance, using only 3 GPIO pins. This is done because the LED is connected to a MAX 7219 driver. The driver is able to take in an address, that being the column or row on which the microcontroller is displaying, and it outputs the specified LEDs to be turned on and off. With that, we can get into the function of the game.
To start the program, you'll press the reset button on the microcontroller. This will bring up a loading screen on the grid. The loading screen emulates a snake moving across the screen in the same way it will during the game. Pressing the yellow speed button will change the difficulty of the game by increasing the speed of the snake. The default state is the medium difficulty. That first button press brought it to hard difficulty, where the snake moves faster. A second button press will bring it to easy difficulty by making the snake update really slowly, and a third button press will bring it back to its default medium state. Once you have a difficulty selected, you will press the blue button in order to start the actual game, which Camryn will show now. The moving dot is the head of the snake, and this is what the directional buttons control. Moving the head of the snake over the disparate LEDs, which represent the food, will increase the length of the snake. In order to win the game, you must fill up the entire LED screen by eating 63 pieces of food. There are 2 ways to lose the game. The first is colliding with any of the exterior walls, and the second is colliding with the snake itself, which Camryn has just showed.
Now, when we press the blue button, this will bring us back to our loading screen.
The loading screen, at this point, you can change the difficulty again and start when you are ready to play the game. Camryn has just displayed how hitting the exterior walls will fulfill the second lose condition of the game.